In previous sections, we saw applications of multiple integrals, and here we're going to see how they can be used to find surface area. We are looking here at a surface in space we're going to call zf of xy, and I'll put a point here in the xy plane. We'll call it xiyi. Associated with that point is a point on the surface, which is xiyi f of xiyi. Now let's consider a little delta A in the xy plane, and it'll have dimensions delta y and delta x, a little rectangle in the xy plane, and associated with that is a little patch on our surface. What we're going to do is we're going to approximate the area of this little patch by considering a portion of the tangent plane at the point xiyi f of xiyi. And here we have that, and as you can see, it is, well, it's part of a plane, right? So it doesn't exactly sit on the surface, but it's going to approximate the area of that little patch. We can consider this tangent plane to be defined by two vectors, A and B. And the vector A is part of a line, the slope of which, or the slope of that segment of a line that forms this edge of the portion of the tangent plane, is the partial derivative of f with respect to x at xiyi. Likewise, the slope of the part that's formed by B is the partial of f with respect to y at xiyi. Now, enough of this setup. We're going to write some things down. If we represent the portion of the tangent plane, which we're going to call delta t, using vectors a and b, then the area of delta t is the magnitude of A cross B. Now let's see if we can write expressions for A and B. I bet we can. A is equal to delta xi plus the partial of f with respect to x at xiyi times delta xk. What? All right. The vector A is above the segment delta x, and it has a constant y value, and so it only reflects a change in x. But it does dip down, and so when I said it only reflects a change in x, I meant x and not y. But in this picture, it dips down. It could point up or be flat. It doesn't really matter. The point here is that A has a j component of 0, but it has an I component that's related to delta x, and it has a k component. And if we think about what a partial derivative is, then the partial with respect to x of f of x sub I y sub I is rise over run in the x direction, and we multiply that by run, which is delta x. The runs essentially divide out, and we end up with rise times delta k, or times k. Delta x sub I is the part that's parallel to the x-axis. In the same way, we have that b is equal to delta yj plus the partial of f with respect to y at x sub I, y sub I times delta yk, where delta y would be the horizontal component in the y direction, and the partial of f with respect to y at x sub I, y sub I times delta I is going to give us the vertical change, and that's in the k direction. Now that we have these expressions, we can write down that A cross B is equal to the cross product ijk, delta x, 0, the partial with respect to x at x sub I, y sub I times delta x, and then 0, delta y, the partial with respect to y at x sub I, y sub I, delta y. The cross product gives us that A cross B is equal to negative fx at xiyi times delta x delta y times I minus fy at xiyi times delta x delta y j plus delta x delta y k. So the magnitude of A cross B is equal to the square root of fx at x sub I, y sub I squared plus fy at x sub I, y sub I squared plus 1 times delta x delta y. Now that's the area of a delta t, a portion of a tangent plane. Finding the area of the surface means we're going to sum together a bunch of portions of tangent planes. Guess how many we're going to do? The surface area is approximated by A is approximately the sum as I goes from 1 to m of the sum as j goes from 1 to n of delta t ij. Aren't you glad we didn't write the whole thing out? Taking limits as m and n approach infinity yields that the area of the surface is equal to the double integral over the region D of the square root of fx of xy squared plus fy at xy, those are the partial derivatives, squared, plus 1 times dA. Or we can write it using partial derivative notation with the curly d's. The area of the surface is equal to the double integral over the region D of the square root of the partial of z with respect to x squared plus the partial of z with respect to y squared plus 1 dA. So to find the surface area, we find the partial with respect to x, square it. Partial with respect to y, square it. Add them together, add 1 to it, put it in a square root. Hope that's something that we can integrate. The region D is the trace of the region in the xy plane.